Hello. In this video, I am going to solve a problem which is chosen from Iran's mathematics Olympiad contest. It's a problem in planar geometry related to the areas of quadrilaterals. So let me describe the problem for you first. So we have a quadrilateral ABCD, just a random quadrilateral, and we partition this side AB into 7 equal pieces, and we do the same thing with the side DC. We also partition it to 7 equal pieces, and then we start joining the partition points one by one correspondingly. Of course, as you see, I will partition the original quadrilateral into 7 smaller quadrilaterals. The question is this: prove that the area of at least one of these smaller quadrilaterals is 1/7 of the area of the original quadrilateral. I recommend you to pause the video at this point and try to solve the problem yourself first. And if you get stuck, you can come back and review and see a proof for this problem. Okay. I really enjoyed solving this problem. The reason is that it seems fairly complicated. Yes, you might think about a lot of relations that you have in your head right now about the areas. But the idea that can solve this problem is actually very, very simple, that you have seen it in all geometry courses, probably elementary geometry courses in Euclidean geometry. So let me just remind you about that problem. So assume that you have a triangle. So let me just draw a triangle here for you. So that's the cornerstone of solving this problem. I have triangle ABC, and then I take a random point somewhere here. For example, let me call it X, and then I join A to X as well. Then you see that I have actually 3 triangles here. But you immediately see that if you draw the height of, for example, triangle ABX, which I'm trying to do here now, so I will get this line segment, AH, and let me call the height to be H. So you see that this height is not only the height of this triangle ABX, but it is also a height for the bigger triangle ABC, and even a height for this obtuse triangle that you see here. Of course, here the base is CX, here the base is BX, and for the total triangle, this would be BC. So the point is that I have 2 triangles with one common height. What we want to show is that the surface area of this triangle, for example, ABX, over the surface area of the original triangle here, for example, ABC, is equal to the ratio of the corresponding bases. So in this case, the base is BX, and for the case of the bigger triangle, the base is BC. So that's extremely simple, yes, because if you start from the left-hand side, so the area of this triangle is 1/2 its own base, which is BX, multiplied by the height corresponding to that base, which in this case is H. And I do the same thing here, but this time the base of the bigger triangle is BC, but still the height is the same. So you see that these are all canceled, and what is left for me is exactly the fraction on the right. So this, if I want to express it in words, I would say that if I have 2 triangles with one common height, then the ratio of the surface areas of those 2 triangles is equal to the ratio of the corresponding bases of those triangles. Yes? So you see, this is very, very simple theorem that you can immediately understand. And one method to solve this problem is using that idea several times. Okay, but of course you might say that we don't have any triangles involved here. Yes, you're right, but it is not a hard thing to do. We can partition quadrilaterals into 2 triangles, and each time we can somehow effectively use that problem and solve this, use that theorem and solve the problem. Okay, so first of all, they haven't mentioned explicitly which quadrilateral they are talking about, but I think if you rely on your instinct, it's not that hard to understand that probably this is our quadrilateral because it's at a unique position among the other ones, yes? So MNPQ. So my goal is to show you, to convince you that the surface area of this middle quadrilateral, MNPQ, is 1/7 of the surface area of the original quadrilateral. So that is my claim. Okay? So in order to do that, how can I use this theorem? Okay, so let us momentarily focus on this smaller quadrilateral that I want to have its surface area. I partition it into two triangles. So that's a very standard trick, yes? Whenever you want to talk about the area of quadrilaterals, so one thing that comes to your mind is to partition it into the two triangles by drawing a diagonal, yes? So I will take my ruler here, for example, and then draw this diagonal. Then I partition my quadrilateral into two triangles. I don't know anything about if they are congruent or not. I don't know anything if they are similar or even about the equal areas. I don't know. So I will call the surface area of the triangle MPQS1 for simplicity of writing just, and the surface area of the triangle on the other triangle S2, for example. Okay, so let me just focus on S1 for the time being, and to make it more clear, so let me highlight it here for you. Okay, one more line I want to add to my picture, and that is the line that I want to connect, that connects M and D. Okay, so what you can immediately realize, so forget about the right part of the picture, only concentrate on this triangle MDP and MQP. You have exactly that scenario repeating itself here. Because I don't want to mess up the picture, but if you imagine that I draw a height here, this height will be a height of this bigger triangle as well as the height of this narrow triangle here. So this means that the ratio S1 over the area of this bigger triangle, which is S of MDP, is exactly equal to the ratio of the corresponding bases. So the base of this narrow triangle is PQ, and the ratio and the base of the bigger triangle is DP, yes, or PD. But because of the construction of the problem, I know that all these line segments are of equal lengths, yes? So this means that the ratio of PQ over PD is 1, but this is 1, 2, 3, 4. So PQ over PD is a quarter. Yes? Okay, so what we learned that the surface area S1 is 1/4 of the surface area of triangle MDP. Okay? I can repeat the argument for S2 by joining this one, by joining P to B. Okay, I join these two, and then let us concentrate on this triangle now, whose area is S2, and compare it with the area of PMB, this triangle. Yes? Exactly the same reason. You see that this problem repeats itself, but in an upside down manner. Yes, this is the vertex here. Okay, so you would say that the area S2 over the surface area of the triangle PMB is equal to the ratio of the corresponding bases, which in this case is MN for the narrow triangle, and MB for the bigger triangle. But again, the same thing repeats itself, yes, because this length and that length, that length and that length, according to the construction and the problem, are equal in size. So this is also 1/4, exactly. So this means that S2 is 1/4 of the surface area of PMB. Now, because I want to say something about the total surface area, it motivates me to add them side by side. So S1 plus S2 becomes exactly the surface area of the quadrilateral that I was looking for, MNPQ. Yes. On the right-hand side, I can factor 1/4 out, and let us try to see what happens if I add these two surface areas together. So MDP plus PMB. I hope that you agree with me immediately that this becomes the surface area of a new quadrilateral, but this quadrilateral is MBPD. Okay, so let me just write this and call it number 1. So we showed that the area of the middle quadrilateral is 1/4 of this quadrilateral, surface area of this quadrilateral, MBPD. Okay? Now, we want to find a connection between the area of this quadrilateral that just popped out, and then to find the relation between that surface area and the surface area of the original quadrilateral. Okay, but to do that, let me, I don't want to distract you, and I don't need this part anymore. I want to clean this one, okay, because we don't need it. Let me take it away so that it does not distract you. Just give me a moment. Okay, so that's good. Now I concentrate on this one. I'm quadrilateral MBPD. Okay, but this time I will draw another diagonal here. I want to join actually this B to D. Okay. Okay. And now to be so again, you really don't need, for the time being, for the first part at least, you don't need to concentrate on what is on the top. Just concentrate here, okay? So what I can say is that what is the ratio of the area of this? You see that again, that problem repeats itself here. Concentrate here on this bigger triangle and with this smaller triangle. Both of them share the same height. I don't want to draw the height, but the height is here. Yes. So what I can say that the surface area of BDP to the surface area of BDC is again equal to the ratio of the corresponding bases. The base of the first triangle on top is DP, and the base of the triangle BDC is DC. But you see that DP is 4 of these parts and DC is 7 of those parts. So the ratio is 4/7. So this means that the surface area BDP is 4/7 of this surface area. Yes? Okay, now what we can do, we can ignore the part below. Yes, we can just ignore that, ignore everything below, and just concentrate here and repeat the argument. Okay, so I don't want to write it more because that's exactly the same thing. But then you see that this total area, you consider this bigger triangle and this triangle here. Again, the same thing. The base of the narrow one is 4 of these, and the base of the bigger one is 7 of them. So again, the same story. So this means that the surface area of dBm is also 4/7 times the area of dBA. Surface area dBA. And now, if I add these two side by side, what will happen? Now, let us look at the picture in its entirety. So, BDP plus dBm exactly becomes the area of the quadrilateral that I had over here already. So S of MPDB, and if I take 4/7 out and then add these two areas together, what do I get? BDC is this big triangle here, plus DBA is this triangle. It's clear. When I add them, it becomes the total area of the total quadrilateral. So this becomes S of surface area of ABCD. Okay, so let me call this number 2. Then hopefully everything becomes clear for you. S of MNPQ from relation number 1 is a quarter of S of MPBD. But S of MPBD itself is 4/7 of the surface area of ABCD. And I hope that you immediately see that these two are cancelled, and I get 1/7 surface area ABCD. So then we eventually were able to show that the surface area here is 1/7 of the surface area of that one. At least we were able to show that this is working for this middle quadrilateral. So I really considered this is a nice problem because it was fairly non-trivial. It was not hard, but it was not that trivial. And the only thing that we used here has nothing to do with complicated formulas or trigonometries related to areas and things like that. We are just using a very simple fact that even you learn it in primary school, because we learn about the areas of triangles in primary schools. So then it means that we in principle can develop this in our head and then use it several times in an effective and efficient way, in a wise way, to be able to solve this fairly nice and non-trivial problem. I hope that you enjoyed the video. So until the next video, be safe and goodbye. Thank you.